Okay, in this topic, we're looking at the projection theorem, which is basically an optimization problem, a minimization problem. It's a way of looking at solving a linear algebra problem. So the minimization problem basically comes down to this. Given some subspace M, we wish to solve this problem, which is the minimization of little m in the set M, such that the norm of y minus m is minimized. We're trying to minimize that norm. Okay, so this minimization problem actually appears in a number of different disguises. This is a constrained optimization problem. We want to minimize this norm of the difference, but we're restricted to the values of m in the set capital M. So this is a constrained optimization problem. So again, we're looking for m in the set M, little m in the set big M, such that for some y not in the set M, we are looking for the one that minimizes this norm. So I'm going to show you a little illustration here that suggests the optimal solution M star is such that the error, that is the difference between y and M star, is orthogonal to every element of M. That is, if y is in M, or rather, if y were in the set M, then the optimal M star, our star player, would be just y. Okay, so this is trivial if y is in the set M. Where it's not trivial is when y is not in the set M. And so this illustration that I'm showing you, so let M be this plane down here. Okay, so this is like the xy plane, and the vector y, or rather this vector y, is out of the plane. Okay, it is out of the plane. It is it's actually a three-dimensional vector instead of a two-dimensional vector. So this subspace M is a subspace of the three-dimensional space, and so this this vector y then, if I draw the shadow down onto this plane, then M star is that vector that's the shadow. Okay, and so the error then, which is the difference between y and M star, that error is orthogonal. It's perpendicular to this plane. Okay, it's perpendicular to that plane. So that's the concept of the projection theorem. So there's a little bit of work to establish this. I'm going to just briefly go through just one of the proofs. I actually have a separate little video here that goes through the various proofs of the different theorems that we're going to be looking at here and lemma. So, but this is the basic idea illustrated. So again, we're looking in general at vector spaces, general vector spaces. So this is not necessarily a matrix problem. This is in general the vector space problem. So the first lemma is, if x and y are orthogonal, then x plus y quantity squared is equal to x squared norm plus y norm squared. So this is, again, this is the Pythagorean theorem for vector spaces. So again, here's the proof. Since x and y are orthogonal, then their inner products are 0. So when we take the norm squared of the sum, we basically do the vector space version of FOIL. So here's the vector space version of FOIL. These guys are both 0, and so the proof just falls out. So many of the proofs are actually follow very step-by-step like this, and you can see those if you go look at the proofs video. So the orthogonality condition. We wish to show that the optimal is such that the error is orthogonal to M. And we're going to do this by contrapositive argument. So when in talking about the proof, we're going to prove this by contrapositive argument. And the contrapositive argument basically would state it this way. Assume the minimizer is such that E, which is the y minus M star, is not orthogonal to M. Okay, so the contrapositive argument basically assumes everything about the thing we're trying to prove except the result. Okay, so we're wishing to show that m star is such that the error is orthogonal to m. So we're going to assume that it is not orthogonal to m. So and then what happens with contrapositive argument is that you assume not the result and show that by assuming not the result, you get a contradiction. So it kind of looks like this. The direct proof would say A, blah, 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 to B. And we just go step by step and prove B. Contrapositive argument says, I'm going to assume A and not B and show that we get a contradiction. So that show that some kind of contradiction. Basically, if you assume A and not B, you get something that you work through that logically, and you find that, for example, that requires that not A be true. And that would be an example of a contradiction. All right, so here's our situation. Suppose the minimizer, m star, is such that the error is not orthogonal to m. This means that there must be some component in m, let's say m naught, where we can assume that that component is of magnitude 1, such that the inner product of y minus m star, that's the error, inner product with that is equal to some value delta, where delta is not 0. Okay, so this is saying these two are not orthogonal to each other. M naught is not orthogonal to delta. So we define m hat then to be m star plus delta times m naught. Delta conjugate. Well, in general, again, since we're assuming things in general vector spaces, we could be looking at complex things, but in which case we would just, if we were looking at all real things, and this would just be delta. All right, so we have this. And so now we look at y minus m hat. So m hat is this, okay? And we compute the norm of that squared. And you can go through and show that the norm of this squared is equal to y minus m star quantity squared minus delta squared. You can actually go through and show that you get this quantity. And this comes out because of the fact that the norm of delta bar m naught is just delta squared, or the norm squared is delta quantity squared. So we actually get a negative sign here. What does this mean? That means the difference between y and m hat is less than the difference between y and m star, which says that m star, gives you a smaller norm than the optimum, the one that gives the smallest norm. So that's a contradiction in that m star is the one that gives the smallest norm, but this m hat, which is an m, gives a smaller norm. So there's a contradiction there. So that shows that the error must be orthogonal to m. All right, given a subspace M, then any element x can be decomposed into the sum of two things. X is equal to the sum of two vectors, xm and xm perp, where xm is an m, xm perp is an m perp. So given any subspace, you can always do this. And since m and direct sum with m perp is the whole vector space, and m intersect with m perp is just the 0 element. So we have this thing, and this is going to be helpful in understanding the projection theorem. So this is some preliminary information that we need in terms of the projection theorem. We'll move on now to talk about the projection theorem.